So first of all, if you want to understand about how to gain more power in your experiments, you need to think about what we call here the noise effect number triangle. And there are different routes to get power. So I want you to cast your mind back, and it might have been a scary time when you first did a course on statistics, or you perhaps first picked up that book to learn about statistics. And you're dealing, it might have been with sort of normal distributions, or it might have been coin tossing like we've done in other parts of this course. You might remember the standard deviation. That's the amount your data it varies from its average. This is often caused by noise of some sort. It might be individual differences between people, or it might be that if you're doing the same thing again, even the same person doing the same thing gets a different result. You might make more or less errors each time. So there's some sort of variability each time you gather data. If you average a lot of data, then that average has less variability. It tends to become more consistent over time. And the standard error of the mean is how much that average varies. So it's your estimate of how accurate your that average is. On a graph, you often put your little error bars on, and that's representing that standard error of the mean. Now, as I said, if you cast your mind back, you might remember the standard error of the mean is, for most distributions, there are some odd ones, but for a lot of distributions, the standard error of the mean is the standard error of a single observation divided by the square root of the number of things you've got. So if you had 4 participants, then the standard error of the average of those 4 participants is going to be 1/2, that's 1 over the square root of 4 of the standard error of one thing. So let's imagine it's heights of people. The standard deviation of male heights in Britain is about 3 inches. So if you had, say, 100 people, then and you took their average height, then the standard error of that, the amount you expect that average to vary, is going to be 3 inches divided by the square root of 100. So that's 0.3 of an inch. So as I said, you might remember that, and I hope that was a little bit of a reminder for you. Crucial thing, because of that square root of n, if you want to half the standard error, you need 4 times as many people. You need to quadruple the number of people. If you want to divide that standard error by 10, you need 100 more people. So then the question is, how big a difference do you want to detect? So imagine we're going to look at the average height of Danish men and British men, and ask ourselves, are Danish men taller than British men? So maybe I get 10 Danish men, 10 British men, and want to compare those. So you're going to work out the average Danish height, the average British height. But the question is, how big a height difference do I care about finding? If the difference in heights, the average height between Danes and Britons, were 0.1 of an inch, perhaps I'd think, well, that doesn't really matter. If it's 12 inches, so that I'm looking up all the time, then I would care a lot. So how big that difference? So let's say we're going to go for half an inch difference as being something we care about. And as I said, the standard deviation for British heights is 3 inches. I'm not quite sure what it is for Danes, but probably not so different. So if I had just, say, 4 British people and 4 Danes, then my average height for 4 people, I take my height, sum them, divide by 4. The standard error of that will be 1/2, 1 over the square root of 4, times my 3 inches, which is my the variation or standard deviation for one person. So that's going to be 1.5 inches. So if the amount my average is likely to vary about is 1.5 inches, I'm not very likely to be able to detect a half-inch difference. I'm going to need a lot more. If I had 100 British people to measure, then my standard deviation, or my standard error, is going to be my 3 inches divided by the square root of 100. That's 0.3 of an inch. I'm perhaps now going to be able to detect my half-inch difference, but it's still pretty close. I probably want it small again. In general, you want the standard error to be a lot less than the thing you're trying to detect, the minimum effect size that you think is important. So let's just look at that. You've got your effect size. You want that to be a lot bigger than that its variability of what you're measuring. It's typically an average. It can be other kinds of statistic. For a normal distribution, for a lot of distributions, that variability is the noise, the standard deviation, divided by the square root of the number of participants. So you can see there's three elements here: the effect size, the noise, the number of participants. Now, when you want to gain power, when you want to make it more likely that you will see an effect, you can vary any one of those three in order to try and improve your experiment. Not just more subjects, it's not just about varying the number. This gives you different strategies for getting more power in your experiment. One is to increase the number, the thing we've already talked about. That's the standard approach. But you notice that square root there. You often needed really large numbers in order to start making a difference. So although it's a standard approach, and sometimes it's the only thing you can do, in general, it's a fairly poor way of gaining more power, just because you have to have those numbers so huge sometimes. There are other advantages of increasing the number. Very often that increases the sort of range and kind of people that you're looking at, and that can be good for other reasons. But it's only one approach. Another thing you can try to do is to reduce the noise in your experiment. Now, this is what physicists do in standard physics. You try and make everything as controlled and as tight as possible. And also a lot of psychology experiments. You remove anything that might cause problems. So if you're trying to measure the thermal capacity of a piece of metal, you'll make sure there's no air currents in the room that might make things go odd. You'll make sure that your material is as consistent as possible. So you can do the same sort of thing with people, and we'll talk about that in a minute. So you can control the conditions. The other thing you might do is you might not be able to control what's happening, but you might be able to measure things that get in the way. So for instance, if you've got lots of people, if you measure their age, if you measure their experience, then you might be in a position to be able to model the effects those have, and then effectively reduce the unknown noise. And then the third thing you can do is to attack the effect. So you can say, can I actually change my experiment or change my study so that the thing I'm after gets bigger? So this is about manipulating the sensitivity. A good example, you've probably all seen of this recently, was the photographs during the inauguration of President Trump. Photographs from the front of the crowd, it was very difficult to see the differences in even substantially different crowds between previous inaugurations and President Trump's inauguration. Of course, the photograph from the back of the crowd was a much more sensitive measure and was able to see differences. Hopefully your experiments may not be quite as well, should we say, problems or controversial as that particular one. But again, you can do the same kind of techniques in order to give yourself more power in your experiments and in your studies.